Dear students, in our last lecture, we talked about Lorentz series. In fact, we derived it in this form. Our expression for Lorentz series was fz is equal to sigma n is equal to minus infinity to plus infinity cn z minus a raised to n, which we can write it in another form. We can write it as sum of two series. One is n equal to 0 to plus infinity cn z minus a raised to n. Another is n equal to minus 1 to minus infinity cn z minus a raised to n. Now this cn is, I will write its value here. Cn is 1 by 2 pi I integral fc f gamma d gamma divided by gamma minus a raised to gamma minus a raised to n plus 1. One advantage of this expression is that you have one cn for both the series, this positive series as well as negative series. But there are other ways people can express this Lorentz series in other ways. One of the popular this expression for it is that is obtained by replacing this index here. Suppose you are having n running from -1 to -infinity. If I can do this change, suppose I change this by letting m equal to -n, replacing -n by m. In that case, if n is -1, then that would mean m is equal to +1. n -1, m +1. Similarly, if n is equal to -infinity, m will be +infinity. And if we change now this index here, we will get n is equal to m is equal to 1, m is equal to 1 in this place, and m is equal to infinity here. And next we get c minus n minus m, because you are replacing n by m minus m. N is equal to minus m. So I write it here, and then z minus a raised to minus m. So I can write this in an alternative way, but that will also change this index here. It will be cm is equal to 1 by 2 pi I integral, or here because the space there is less, so c minus n minus m, n will be replaced by minus m, so it will be 1 by 2 pi I integral f gamma d gamma divided by gamma minus a n plus 1. N is to be replaced by minus m plus 1. So minus m plus 1. So the two indices will now be different, slightly different. Difference will be in this power here. There's one more thing, that when I suppose now I do one thing, since this is true for this index m, I can replace this index m once again by n. I can write n is equal to 1 to infinity, n is equal to 1 to infinity, c minus n, here minus n, z minus a raised to minus n. M was a dummy index, and I have replaced it once again, and then I can use this as part of Lorentz series. That too is possible, but this first expression is the simplest, most concise, and it has the advantage that you have to remember just one CNN, one CN. Anyhow, we can use this form or that form. Uh, uh, that does not matter. We will now address some. We will have some practice with some problems based on Taylor series and Lorentz series. Let us first of all take problems on Taylor series. In Taylor series we have fz is equal to fa plus you are expanding about a f dash a, then z minus a, because you are expanding about a, plus f double dash a z minus a squared divided by 2 factorial, and so on. Suppose we start with three simple expressions which we will be using frequently. One is fz is equal to e raised to z, exponential function e raised to z. Now it is quite simple. About z equal to 0. Z equal to 0, that means I will require these values f0. F0 is equal to e raised to 0. That is 1. Simply 1. Then f dash, first order derivative is e raised to 0, e raised to z. Derivative of e raised to z is e raised to z. Then f dash 0 will be e raised to 0, that is 1. F double dash z is equal to e raised to z. F double dash 0, that will be 1, and so on. All the coefficients will be 1. Then fz, that is this e raised to z. Fz is e raised to z. E raised to z is equal to fa. Fa is 1 plus f dash a, that is 1 z minus a plus f double dash a, that is again minus 1, that is again 1. So it will be 1 by 2 factorial, 1 by 2 factorial z minus a squared. But a, as we have decided that we will take a 0, so we need not write here a, because we are expanding it about z equal to 0. So we will have here z, then here 1 by 2 factorial z square plus dot dot. We will have to remember this because we will be using this time and again. We will be using this. So we hope that we remember it. Such expressions should be memorized. Better it is to memorize them. They are frequently used in mathematics and physics. Now, then there is another, that is, let us take now the same by Taylor's theorem. Fz is equal to fz is equal to fa plus f dash a into z minus a plus f double dash a into z minus, divided by 2 factorial z minus a squared plus dot dot dot. Okay. Now here fz is equal to sine z. Now therefore we are expanding about z equal to 0. So it is f0 is equal to, a is here 0, f0 will be sine 0. Sine 0 is 0. Then we have f1, f dash z. F dash z is equal to cos z. F dash 0 will be cos 0, that is 1. Cos 0 is 1. F double dash z will be equal to minus sine z. That will be f double dash 0 will be 0. You can see first term 0, this 0, then again third term 0, odd terms will go, and then f triple dash z is equal to minus cos z, f triple dash z is equal to minus 1. Similarly f4z, now it is better to write these numbers. f4z is equal to minus sin z. Again f4z is equal to 0. f5z is equal to minus cos z. f5z 0, sorry, these are zeros, 0 0, that will be minus 1. So enough. Now therefore in this place we will write, f this sin x, sin z is equal to fa f0, that is 0. Then f dash a 1, z minus a, that is z, because we are expanding about z equal a equals 0. That is z plus, this term won't be there because f double dash, that is 0. Next term will be there but minus, with minus sign, minus z cube, that will be cube term, and it will, that term will have f triple dash, yes, f triple dash 0 minus 1, that is minus 1 divided by, it will then have 3 factorial, just as this has 2 factorial, that will have 3 factorial, and z cube. Then next f4, that won't be there because this is 0. Then f5, that will be there, that is it will be again minus okay, it is minus cos z, that gives minus sin z. Minus sin z will give plus cos z, sorry, plus cos z, this plus 1. So plus terms will be alternatively positive and negative, and it will be, since it's fifth term, so it will be 5 factorial z5 minus dash dash dash. This is sin z. So we now take up last, as a last example of this will be cos z again. Cos z about we have, again let's first write this, no need to write it, you can now easily remember it, as fz is equal to here is fz is equal to cos z. Then f0 is equal to cos 0, that is 1. f dash z is equal to minus sin z, that is equal to f dash 0 is equal to that is 0. f double dash z is equal to minus cos z, f double dash 0 will be equal to minus cos 0, that is minus 1. f triple dash, let us write 3z is equal to minus sin z, f triple dash triple z is equal to triple 0, that will be equal to 0. f fourth this fourth order derivative will be equal to minus cos z, that will be f fourth order derivative, f40 will be minus 1, and so on till we reach this. We can write now we can write cos z is equal to f, first of all this f0, that is 1. Then next term won't be there, the even terms will not be there. Then this minus 1 divided by 2 factorial z square. Then we have third, this term won't be there, then it is it will be, say it was minus cos z differentiated and it became minus sin z, becomes cos z. Okay, then it's again minus 1 by this is the fourth term, 4 factorial z4, and so on. I think you should check this sign here. Somehow I suspect that it should be positive. First positive, then negative, then third positive. Is, let us go from this term cos z, that is minus sin z. Minus sin z goes to cos z. Okay, cos z and minus sin z. Now cos z to plus. Yes, there was this. So it is plus. So you have these 3 series that I will collect them here. I will write them here on this page. I will have first e raised to z is equal to e raised to z. We had here 1 plus z square by 2, etc. 1 plus z 1 plus z plus z square by 2 factorial plus z cube by 3 factorial plus dash dash dash. Then we had sine z was equal to, back to sine z, it was sine z was equal to z minus and then all terms z, it is z plus all term z cube by 3 factorial, then again next odd term but with positive sign z5 by 5 factorial plus minus z7 by 7 factorial and dot dot dot. Now then cos z is equal to 1 minus z square by 2 factorial plus then z4 by 4 factorial minus z6 by 6 factorial plus dot dot dot. Now these we shall be using them, so that's why I have written them here, so that it is for future reference we can quickly go to them and then test them. Now let us go for one more problem, that is suppose I have fz is equal to e raised to z not e raised to z divided by 1 minus z. I want to give this Taylor series expansion of this. Now obviously it will be a series expansion of e raised to z. We will go for series expansion of e raised to z divided by this series expansion of 1 minus z. Now these terms, for example you have 1 minus z here. Look at this 1 by 1 minus z. This reminds us of that geometric series 1 by 1 minus x, which is equal to 1 plus x square plus x cube plus dot dot dot. Provided of course if mod x is less than 1, then this is then this sum of this infinite geometric series, provide mod x is less than 1. Similarly you have here 1 by this 1 minus z, 1 by 1 minus z, which can be easily written as this series. No need to use this Taylor series directly. We use other tricks, shortcuts, instead of directly going for Taylor's or this Lorentz series, especially Lorentz series. We make those what we call mathematical this trickery that is used in order to avoid Lorentz series these quotients. Similarly, let us first go to this. We're talking right now about this Taylor series expansion. Now, this series expansion 1 by, I can write it as 1 plus x, 1 plus z square plus z cube, but there is a caveat, that is this z mod z should be less than 1. Should be less than 1. Now less than 1. Okay. Since you are expanding about this about z equal to 0, this is z equal to 0, because otherwise had it not been an expansion about z equal to 0, then that factor would have been here. For example, an expansion about z equal to 1, that will be z minus 1, z minus 1 square, z minus so on. Now z equal to 0, z equal to 0 is center of this expansion, and z equal to 1 is the singularity. We have singularity of this at z equal to 1. 1 by 1 minus z. Now this is z equal to, you can see z equal to 1 is singularity. So 1 divided by z minus this is valid, then this function can be expanded only within this circle. The disk is it is, I mean, convergence disk. Convergence disk is, sorry, this is 1 1 as disk of radius 1. We are expanding about this, and see, now you can yourself see in this disk z is certainly less than 1. Mod z, I mean, mod z is less than 1. Here it is mod z less than 1 as long as you are on the disk. So we can certainly, then we are allowed to expand it. We can expand it as 1 plus z square plus z cube plus dot so on. And if we expand now e raised to z, if we expand e raised to z, that is equal to 1 plus z square plus z cube by z square by 2 factorial z cube by, I had written it here, it is 1 plus z square by 2 factorial 1 plus z square by 2 factorial plus z cube by 3 factorial plus dot dot dot. Now you then, if you have, now you have ez divided by 1 minus z. When you write both expressions, the problem with it is simplification. Then it is very difficult to simplify it. Now there is another method in which what we do, we can do one more thing that we can do for this is that we write, for example, we have e raised to z divided by 1 minus z. I write like this. I say its expression, since it can be expanded in Taylor's this series, so that let that series be a naught plus a1 z plus a2 z square plus dot dot dot. The question is, I need to determine these quotients a naught, a1, a2. I think you must have understood what is my point. I mean when you write ez divided by 1 minus z, the problem is that if you write its expression here and expression of this here, then both are long expressions, and it is simply not possible to simplify them easily. Now I don't know whether they can be simplified even. Now you have this. So what I do, I use an alternative method. That is, I write that since both of them can be expressed in Taylor series, then I can write Ez divided by this equal to this Taylor series. Now about z is equal to 0, of course, and in that Taylor series, a naught, a1, a2, these are coefficients. Now I have to determine now these coefficients. Once I determine these coefficients, this means that I have determined this. So for that matter, what I will do, I will multiply both sides by 1 minus z. I write e raised to z is equal to 1 minus z into a naught, this a naught. It is better to not multiply this, rather I have to write this. I can write, if I write 1 minus z, okay, yes, no problem, a naught plus a1 plus a naught plus a1 plus a1z plus a2z square plus dot dot dot. Okay, now what I do, I write expression for Ez, this Taylor's expression for Ez, and Taylor's expression for e raised to z is this. So I write here 1 plus z square by 2 factorial plus z cube by 3 factorial plus dash 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 dot dot. That is, and I multiply this with this. So if I multiply this with this, and then what I do, I collect these coefficients of these similar terms. Now suppose, for example, I have here this one. In place of 1, I will get here, when I multiply this, if I multiply this with 1 into, say for 1 into a naught, so I will have here a naught instead of 1, and then 1 into this, that will leave it as such. 1 into this, that will leave. 1 will not create any havoc here. Now so far as this minus z is concerned, now when I multiply by this, then I have minus z a naught minus z into that is a square, that a1 z square, then a z cube plus all that. Now if I compare now these coefficients, say I write, let me first multiply it. This is a naught plus a naught plus a1z plus a2z square plus dot dot dot, then this minus z minus a naught z a naught z minus a naught z, then minus a1 z square a1 z square z square a1, it is a1 here, plus I have then a2 z cube minus, it's not plus, it is minus a2 z cube, and so on, so on. Now what I next do, I compare the coefficients. I compare their coefficients and I get a naught equal to 1, a naught equal to 1, a naught equal to 1, and then I write a1 equal to, that a1 is the coefficient of z, but there are two terms, z terms, one is a1z and minus a naught z. So coefficient is a1 minus a naught of z, and here coefficient is 1. This means that a1 minus a naught, a1 minus a naught is equal to 1, is equal to 1, and where from I can get a1 minus 1, this is minus 1 because a1 minus 1 is equal to 1, or a1 is equal to 2, a1 is equal to 2. Similarly a3, now come to a3, a2, sorry, a2, this is a2 here, a2, and this is perhaps a2, yes, a2 here, this is a1, I had a1 z square. Okay, no, sorry, actually we are comparing coefficients of similar terms, that means x similar powers, z raised to 1, z raised to 1. Now z square, now we have to take up z square. Z square is a2 here, z square is a1 here. So a2 minus a1, a2 minus a1 is equal to, that is equal to a2 minus a1 is equal to how much is that? Let us see. It is of course, here you have this 1 by 2, a2 minus a1, 1 by 2. Where from you can, since you know a1, you substitute it here, a2 minus a1, a1 is 1, a1 is 2, 2 is equal to 1 by 2, that is a2 is equal to 1 by 2 plus 2, that is 5 by 2, and so on. Similarly, you can determine these coefficients, and then when you substitute back here, you get this expression a naught. A naught is 1 plus, then a1 is a1 is 2 plus 2 plus 2 z, then you have, just a minute, then this is z here to z, then you have next is a2 plus a2 is 5 by 2, 5 by 2 z square, and so on, so on. This is the way you can you are advised to check. I can make mistakes, so please do take care of that. Rest of the procedure you must have understood. This is one of one of powerful methods of expressing such things. It is particularly important when the two functions are much more complex than what I have shown you. Now next I have e raised to z. For example, I have no this suppose I have this, let me take fz is equal to 1 by minus 4 into 1 plus z minus 4, z minus 5, z minus 5 by 4. We have to z minus 5, this is like this, z minus 5 by 4. We have to expand it around z equal to 5. It is given that you have to expand it around z equal to 5. Here is the, let us first draw this. Here is the situation. This is 1, 2, 3, 4, 5. This is 5. Now, this expression, you can see yourself where it can have this. Does it have a 0? Yes, let us see whether it has 1 plus z minus 5. Does it have a pole? Sorry. 1 plus z minus 5 divided by 4 is equal to 0. What will make this denominator 0? Minus 4 is a multiplicative factor. Then we have z minus 5 is equal to 0. That means z is equal to 5. It has a singularity at 5. So cannot, if it has a singularity at 5, z equal to 5, says z equal to 5, that it cannot have singularity at z. Sorry, I had forgotten this. I have to take this here, z minus 5 divided by 4, z minus 5 divided by 4 is equal to minus 1, minus 1. That is z minus 5 is equal to minus 1 into 4 minus 4. Z is equal to minus 4 plus 5. That is equal, z is equal to 1. Z equal to 1. At z equal to 1, it will have singularity. Now you can check it here. Put z equal to 1 here. 1 minus 5. That is minus 4. Minus 4 divided by 4. Minus 1. 1 minus 1, 0. Yes, it is there is a singularity there. At z equal to 1. Here is the singularity. This is the singularity. But you are expanding about this. About z equal to 5. Now, you have this situation now. This is your radius of this convergence, this circle of convergence. It should be slightly to this side, and then you have you now have, see, inside this you can of course use geometric series provided of course. Let's first do one thing, that is let's bring it in the form of that geometric series. I can write fz is equal to this 1 by 4, 1 by minus 4 can be taken to the this numerator. You can write minus 1 by 4 there, divided by, let us leave this apart, z plus 1 plus z minus 5 divided by 4. Now there is still one thing lacking, that is it should be our geometric series has 1 minus x. It is 1 plus, so I will change the sign. That will be minus 1 by 4 divided by 1 minus that is, we can either write 5 minus z, or we can keep this minus into minus z minus 5 divided by 4. Now this now becomes 1 minus x. X is this, and you can expand it, provided you can expand in geometric series, provided z minus 5 divided by 4, along with of course minus, but minus mod, that will go because of mod. If this is less than 1, if this is less than 1, that means z minus 5 mod should be less than 4. That should be less than 4. That means z minus 5, that means radius of the circle which has center at 5 should be less than 4. Is it? The question, is it? Yes. It is 1, 2, 3, 4, less than 4. That means just touching 4. That means, but we have the disk has less than 4. It is okay. It does satisfy our condition. Now we can expand it. In geometric series, we can expand it. We can write minus 1 by 4 into now this. Now you know 1 by 1 minus x is simply, it is simply 1 minus 1 by x is simply equal to 1 plus, I'm sorry, 1 divided by 1 minus x is simply equal to 1 plus x square plus x cube, and so on and so on. Now that will be here 1 plus x, but x is itself minus, so it will be minus z minus 5 divided by 4 plus, then next it will be x square, that is square of this, that means z minus 5 divided by 4 squared, and so on. So you can now do it. Powers of this z minus 5. You see it. That is how we do it. Next, let us now turn to this. For example, we have something like this, say e raised to z divided by cos z. I will simply hint you that I will give a hint that you again have to use that method of undetermined quotients. That is, you express it as a naught a1 z plus a2 z square plus dot 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 something like this, and determine these quotients. Now, next, let's now have some problems from Laurent series. You will be surprised to know that we will hardly use this the expression for its quotients here in addressing these questions about Lorentz series, this expansion. For example, let us look at this. We have a function fz equal to 1 by z plus 1, z plus I. Now, complex plane is here. This is 1, this is I, and we have this situation. This is the complex plane, and then I'm sorry, this diagram, of course, you may please tolerate this. Center is at z equal to 0. There is this center, and you can have radius of this convergence at the most 1. It is less than, it should be less than 1. Now, within less than 1, this can be expanded as Taylor series. Beyond that, you can expand it as Lorentz series. So it admits both series expansions, Lorentz as well as Taylor's. In fact, Taylor series is one one special case of Lorentz series. Let us go for Taylor series expansion for it. See, it will have Taylor series expansion in this region, z greater than 0, z greater than 0, less than 1. In this region, let us see, can we expand this? Does this satisfy this condition? Let us see. Fz is equal to 1 by, say, if I take this, if I take z common, 1 by z into, I will get 1 plus I by z. If I write it this way, then since this now I by z, that will be my x of geometric series. Whatever mod of this, mod of I is 1, modulus of I is 1, divided by modulus of this z, that is radius of the circle, 1 divided by this. Since radius of the circle is less than 1, this is 1 here, and radius of the circle is this, less than 1, so it really satisfies this condition. So I can expand it in Taylor's series expansion. Now look, there is an interesting thing. Suppose I had done this thing. I had taken I common, 1 by I, and then written 1 by I. When I take I common, then I have z by I plus 1. In that case, I have 1 by I into 1 by 1 plus z by I. Now the interesting thing is that this cannot be expanded as geometric series within this. Why? Because it doesn't satisfy that. How do I know? Because z now is in numerator, so I is in denominator. Yes, I'm sorry. This does not satisfy. I'm sorry. This does not satisfy this condition. It is I is 1, modulus of I is 1. That is, it is 1 by something less than 1, z. Mod z is less than 1. So this is greater than 1. This is greater than 1. Not less than 1. This is less than 1. Z by I. I is 1. I is 1. This is, for example, I. This is 1. I is 1. That is why it is modulus is 1. And Z is the radius of this. And Z divided by 1. That is less than 1 here. This is less than 1. I'm sorry. So I was wrong. And these things are very important. You have to check. You cannot just go on and expand anything in geometric series. So this will allow you to expand in this region. And when you expand it in this region, you get that is then simple. You get I don't have space here. That is the problem. While teaching on tab, this is the problem. You don't have enough space. Now let me go to the next page. That is fz is equal to say I had taken I common 1 by I, then I wrote z by I 1 plus z by I, yes, that is I back I plus z, z plus I. Now this is less than 1, then I can expand it like this: 1 by I into this, treat this as minus x, minus because minus x, this will be treated as minus. So expand it now: 1 plus x square x, 1 plus x, but since x is minus, z by I, then plus square of this minus z by I square, that is z square divided by I square, and so on. You can simplify and other things that I leave to you. Now what about this region outside this? Now you have this region. This is here. It is 0 here, and this is 1. This is 1. Okay. Now there was a singularity here at this point. What about this region, which extends, of course, from this? It extends, of course, from z greater than 0, greater than 1, less than infinity. This is an annulus, a sort of annulus bounded by these two. In this annulus, you can use this Lorentz series. And for Lorentz series, again, you have I will not see. Now we don't directly use Lorentz series. We don't bring Lorentz series and expand it. Rather, see how it is, how things change now. You have fz equal to, now I had original fz was 1 by z plus I. Now this time what I will do, I will not take I common, I will take z common. Inside I will be left with 1 plus I by z. Now one is one is this it is values I is its modulus is 1 divided by z, 1 divided by z. Okay, now this is of course now less than 1, so it means that we can it is greater than 1, sorry, greater, that should be, z should be greater than 1, so it satisfies this condition for this. Now if I take that this condition and use now geometric series, I get 1 by z into 1 minus I by z, that is equal to 1 minus I by z, then square of that, plus I square by z square, then minus I cube by z cube, plus dash dash dash, something like this. Important thing that you need to know is that this series, look at this series, while as that series, Taylor's series, had a positive power sub z, positive, then 3, then 4, positive power sub z. This Lorentz series has negative power sub z. So actually Taylor, if we think that, if we say that this Taylor series is, and that's a fact, this Taylor series is one part of the Lorentz series, then what is important is to realize that Lorentz series has then two parts. One in which function is expressed in powers of this positive powers of z, and the other in which is expressed as negative powers of z. Negative powers of z. This is Lorentz expression. I hope you understand this thing. Good. Now, next is, let us take another example. That is fz is equal to z plus 1 divided by z cube plus into z cube into z square plus 1, z square plus 1, z square plus z square plus 1. We have to expand it in two regions. There are two regions now. One is the as usual as we had initially. First of all, let's see where is the singularity. One is at z equal to 0, z equal to 0. A third order singularity, because power is 3, third order singularity z equal to 0. And then there are two more singularities, z square plus 1 is equal to 0. That gives z square is equal to minus 1. Z is equal to plus minus I, because you know that is minus 1 is I, plus minus I. Now you have then this is the complex plane. First singularity is at this z equal to 0. This is one singularity. Next singularity is at this z equal to 1. That is this. There are singularities and singularities, and then this is the circle around this. Now I have to expand this about z equal to 0. Z equal to 0. The problem is that there is a singularity at z equal to 0. However, we can expand it around z equal to 0 by using this Laurent series that allows it. Now, but using Laurent series, I have to expand it in terms of Laurent series. But for Laurent series, again, I won't directly use Laurent series. Rather, once again, I will take advantage of geometric series. So I will do this thing. I will write fz is equal to say fz is equal to z plus 1 z plus 1 divided by z cube. If I take now rather this is better to take this common, 1 plus z, write it 1 plus z by z cube. Okay, then you have this 1 divided by z square minus 1, that is 1 plus z square, 1 plus z square, which I will write as fz is equal to, I have two series now. One is this, and there is this. I will treat them separately. Let me take this one by this 1 by 1 plus z square. 1 plus z square. That is, if I take this one common from this, if I take one common from this, I can write it, or I can write simply nothing is to be taken common. 1 minus z square. 1 minus. Treat this as x. 1 by 1 minus x, and expand it. It will be 1 minus z square plus z4 minus z6 z cube. Sorry. It is 1 minus, first of all, I'm sorry. Yes, it is 1 plus x square plus x square. 1 plus x square plus x cube. But here the problem is that it already has square, so it will appear here 1 minus z square. There it will have z4, but positive z4, and so on. You can better write it beyond that, minus z square. Okay, I have expanded it in terms of this. Now what remains is this 1 plus z by z cube. That is simple. It is simply 1 by z cube plus z by z cube, that is 1 by z square. So I have two branches now. A branch that gives me this in terms of this expansion, in terms of this Laurent series, basically negative Laurent series, and this is a positive Laurent series. Then multiplication product of these two. Now next, suppose I have this situation. I have fz equal to 1 by z into z minus 1. I have to expand it using Laurent series. Two regions. It has two these, z equal to 0 and z equal to 1. These are two singularities, poles. Z equal to 0, there is here it is, and then it is 1 z equal 1. If we go for this region 0 to say, we will avoid this singularity by taking z minus, we have to expand it about, say we will expand it about z equal 0, about z equal 0. So I will do one thing, that is I will again take it as 1 by z into 1 by z minus 1. That there I will write, if I take z common, then no, I will take I will write it as minus 1 or minus 1 by z. That gives me 1 minus z here. And now I have just to check whether z is mod z is greater than less than 1, sorry, less than 1. Mod z less than 1, yes, here in this annulus, mod z is greater than 1, less than 1, sorry, I can expand it. I have minus 1 by z into you have now 1 plus z, 1 minus 1 plus z square. I was perhaps making some mistakes. You will excuse me for all that, because when it is minus, it is minus. This is plus. These are plus only when this is minus. Okay, anyhow, if I have committed any mistake, please do rectify that. Now this is its one, this expansion. In this, so far as this region is concerned, there is no singularity in this region as well, in this region, and one can expand it by using Lorentz force in that region as well. The only requirement is that you must have z greater than 1, greater than 1. But for that reason, you will have to express it here like this. We have to write this 1 by z into z minus 1 is equal to, you will have to write it as 1 by then you have to this is z, this z, and take z common, another z common. You have 1 minus 1 by z. Now z is greater, this I mean 1 by z here is 1 by z. Here it will be that will be less than 1, less than 1. That gives us z greater than 1. This is less than 1. Okay, less than 1. 1 by z less than 1. Yes, because you are here 1 divided by z. Yes, divided by z, that's less than 1, and mod z is greater than 1. Mod z then greater than 1. Yes. Uh, mm, yes, okay, it is okay. Now mod z is greater than 1, and then we can expand this. Again, we have 1 by z square using geometrical series again, and then that you know how that is expanded. The important thing is that in all the cases that we did, you must have noticed one thing. We never used those coefficients of Lorentz series C, and we never used them, or A and B, and we never used them. We used, most of the time we have been using geometric series. Now in important thing is that in geometric series, important thing is that you can use geometric series, but you have to ensure that this term 1 minus x term should be greater than 1. That is important. Okay, let us go now to another last example of this Lorentz series expansion of 1 by sine z. 1 by sine z. So fz is equal to now 1 by sine z, and about z is equal to pi, for example. Of course, we have the sine z. Let us first see where are the singularities. That can be done by putting sine z equal to 0. When you put sine z equal to 0, it gives you z is equal to, when sine is 0. So first sine is 0 at 0, then at pi, then at 2 pi, then at 3 pi, and so on, positive as well as negative values, positive negative values. So it is n pi, we should say n pi, positive or negative values. So if I show them here, then it is 0 here, pi here, 2 pi here, 3 pi here, and so on. Now I have to expand this this about z this pi, z equal to pi here. If I want to expand it about this pi, there should be a region that where this should not have any singularity. The region that is available to me is this. It has the radius of pi. Pi is its radius. Now I want to expand it in this region. Okay, now it is again, you know, it is basically the function is squeezed between two singularities. So I will use this Lorentz expansion. I will expand it about this z equal to pi in this circle where it is radius will be z minus pi. Radius of convergence will be greater than 0, less than pi, less than pi. Okay, I will make a substitution. I will write let t equal to, that will simplify things, t equal to z minus pi, giving z equal to pi plus t or t plus pi. And if I substitute that here, I get sine z is equal to 1 by uh, 1 by sine, in place of sine z I have t plus pi, but t plus pi is 1 by sine t plus pi. That is simply that changes sine of psi is minus sine t. I will do one more thing, that is I will multiply it by t and divide it by t. Multiply and divide both, and I will write sine 1 by sine t, 1 by sine t. Okay. Now what I am going to do is that I will keep this t here. Let this be here, 1 by t into this t. Now what I am going to do, a coefficient of that, I have this, I cannot use now geometric series here. I will do this thing, 1 by t, and then for this I will write a naught plus a1t plus a2t, and you know how that can be solved. You have to multiply this, take this sin t here, expand, put it is this Taylor's expansion there, and then equating the coefficients. I will leave that to you. You can easily do that. I am 100% sure that it is quite easy for you. And then that is the end of this lecture. We will now go to explore singularities of functions. Okay.